Moving along to series and sequences. A sequence literally is a function whose domain consists of consecutive positive numbers. Each corresponding value is a term of the sequence. Let me give you an example of what this means here. I'm going to give a sequence that's a very famous sequence, the Fibonacci sequence, and that is the sequence 1, 1, 2, 3, 5, 8, 13, 21. Basically every term is the sum of the previous two. So we start with 1 and then put another 1, but then 1 plus 1 is 2, and 2 plus 1 is 3, and 3 plus 2 is 5, and 5 plus 3 is 8, and so on and so forth. Now, when it says a sequence is a function where the domain consists of consecutive positive numbers, what I kind of think about this is that the x's are the position 1, 2, 3, 4, 5, 6, 7, 8, and my f of x's are the number. So we kind of think about this in terms of x and f of x, or if I want to think about it in terms of x and y, my x is where it is, and my y is what it is. And that's kind of what I want to think about it. X is where it is, and y is what it is. Now, we are going to kind of redo this whole xy thing a little bit later. We're going to use a different but similar sort of notation for that. Now, two kinds of sequences. You can have a finite sequence in which there are a limited number of terms. So the sequence kind of 3, 6, 9, 12 is a finite sequence, and an infinite sequence where there are an unlimited number of terms. So I can make that sequence up above become unlimited just by putting a dot 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 at the end, and that means that that pattern is going to continue forever. There are also two primary types of sequences, although there certainly are many. The Fibonacci sequence that we did up here is neither arithmetic nor geometric, but an arithmetic sequence is a sequence that you get by adding. So it says the difference between any two successive terms is constant, and we get an arithmetic sequence by adding a number to the previous number. And the number that you add, in other words called the constant difference, is actually called the common difference, and we give it a letter D. In an arithmetic sequence like the one we just did right here, I would find the common difference by subtracting one term minus the previous term. So if I want to think about this right here, I would just take 6 minus 3 and 3, and that would be my common difference. My common difference is 3. So I subtract one term minus the previous term. Now, another type of sequence is called a geometric sequence, and that's a sequence where the ratio of every pair of successive terms is constant. In other words, we do a geometric sequence by multiplying. A geometric sequence is essentially obtained by multiplying. And when I take a term, so when we find the common ratio, you take a term and divide it by its previous term. So one way to think about that, I could do a sequence like 3, 9, 27, 81, and if I take any term and divide it by its previous term, 81 over 27, I get 3, and that would be my common ratio. Finally, some notation. The nth term of the sequence denoted T of n. This kind of gives us ordered pairs that look like this, n, T of n, where n is position, which means where the term is, T of n is value, which means what the term is. And looking way up at the top, and we kind of talked about x is where it is and y is what it is. Well, x, we're not going to use x, we're going to use n. And y, we're not going to use y, we're going to use t of n, kind of like f of x. Now, for the first task, we're just going to look to see whether each sequence is arithmetic, geometric, or neither. And depending on what it is, we're going to fill in the sequence, and then if there is a common difference or ratio, we're going to say what that is. So my numbers here, I have 24, 17, 10, and 3. Well, the pattern is that we're obviously subtracting 7 from each of these. So if I continue to subtract 7 from 3, I would get negative 4 and then negative 11. And if I take any term and subtract, I would get my common difference. My common difference is negative 7. D is equal to negative 7. And that tells me that this sequence is arithmetic. So it's an arithmetic sequence with a common difference of negative 7. This one, 20, 40, 20, 10, 5, if I keep going, every term is half the one before, so this would be half of 5, and I'm going to write it as a fraction. That's 5 halves, and this is 5 fourths. And if I take any term and put it over the one before it, I get 1 half. I can check with a few of them, like 5 over 10 is 1 half, or 5 fourths over 5 halves is the same as 5 over 10, which is 1 half. So this is a common ratio of 1 half, and that means that this thing is a geometric sequence. Geometric because I'm multiplying by 1 half to get to the next term. Now, we got this one, 1 half, 1/3, 1/4, 1/5. I could fill this in. This is 1/6, 1/7. Is this arithmetic or geometric? Well, I can try to see if it's arithmetic. I can do 1/3 minus 1 half. And if I do 1/3 minus 1 half, that is negative 1/6. And then I'll try 1/4 minus 1/3. But that is negative 1/12. So it's not arithmetic because I don't have a common difference. I could try 1/3 divided by 1 half, which is 2/3. And I could try 1/4 divided by 1/3, which is 3/4. That does not give me a common ratio, so this is not geometric. So we just say that this is neither. It's neither arithmetic nor geometric. Okay, then I have negative 1/6, negative 1/3, negative 1 half, negative 2/3. This is really hard to try to compare these. Why don't we try rewriting these with common denominators? So negative 1/6, negative 2/6, negative 3/6, negative 4/6. And then if I make this negative 5/6 and negative 6/6, negative 6/6 is just negative 1, I can continue the pattern. Now, what am I doing to get from one to the next? Well, to get from here to here, I'm subtracting 1/6. I can prove that by saying negative 2/6 minus negative 1/6 is negative 1/6. So that's my common difference. That is a D of common difference. And that means that this sequence is arithmetic. Number 5, I can see that they're all radical 6s. This is negative 5 radical 6, negative 1, positive 3, positive 7. To get from one to the next, I'm adding 4 root 6. And then here I'm adding 4 root 6, and here I'm adding 4 root 6. That means that this is the common difference. I don't really have to show the subtraction to do that. I can just look and say I'm adding 4 root 6. So this would be 11 root 6 and 15 root 6. If it's a common difference, that means that this sequence is arithmetic. Lastly, in number 6, my exponents are changing, but my bases are remaining the same. And we know that when we multiply with the same base, we add the exponents. So what's happening is, I can kind of think of it like this. I'm going to take 5 to the 7/3 over 5 to the 1/3, which gives me 5 to the 7/3 minus 1/3, or 5 to the 6/3, or 5 to the 2nd. And then I'm going to just do that with another set. Let's do 5 to the 13/3 over 5 to the 7/3. That's going to give me 5 to the 13/3 minus 7/3, which is 5 to the 6/3, or 5 squared. this is a common ratio of 5 squared, which is also 25. I'm just going to leave it as 5 squared actually. So knowing that, this is a geometric sequence. Now, that was probably harder than actually figuring out what the pattern is of the exponents, because clearly we're adding 6 thirds every time. So this would be 5 to the 25 thirds, and then this would be 5 to the 31 thirds. So, okay, let's flip it around to the back. The next set of questions asks me to find the first 4 terms of the sequence with this given formula, and to tell whether it's arithmetic, geometric, or neither. To do this, I just need to do some substitution, or I can think about it like a t-chart, because this is like a formula. And the first term is going to be when n is 1, what is t of n? So when n is 1, t of n is negative 5 times 2 raised to the 1 minus 1, which is negative 5 times 2 to the 0, which is negative 5. Next we're going to do n is 2. So negative 5 times 2 to the 2 minus 1, or negative 5 times 2 to the first, or negative 10. The next one's 3, so negative 5 times 2 to the 3 minus 1, which is negative 5 times 2 to the second power, or negative 20. And then finally, negative 5 times 2 to the 4 minus 1, or negative 5 times 2 to the third power, which is negative 5 times 8, or negative 40. This is clearly a geometric sequence. And I can go even further by saying it's a geometric sequence with an r equal to 2. I'm multiplying by 2 each time. Next, we're going to do the same thing. I'm going to set up kind of a t-chart here with an n and t of n, and I'm going to put 1, 2, 3, 4. And let's see, if I plug 1 in, I get 1 minus 7, which is negative 6, and that would be negative 3. Plug in 2 in, so I have 1/2 times negative 5, or negative 5 halves. Plug in 3, so I get 1/2 times 3 minus 7, which is 1/2 times negative 4, or negative 2. And 4 plugged in would be 1/2 times 4 minus 7, which is 1/2 times negative 3, or negative 3 halves. Now, what's happening here is that to get from 3 to negative 5 halves, and then to 2, I'm adding 1/2 every time. So I can think about this as an arithmetic sequence with a common difference of 1/2. Now, we don't have to show this with a t-chart. I'm going to show another way to show the same thing. Instead of saying 1, 2, 3, I'm going to put t sub 1, or t of 1, and that's equal to 1 root 1. And then t sub 2 is 2 root 2. T sub 3 is 3 root 3. And t sub 4 is 4 root 4. In that scenario, this thing here acts like f of x, the way we kind of did it. Instead of saying f of x, I'm saying f of 1, f of 2, f of 3, f of 4, and this makes it very, very similar. So anyway, simplifying this, this is equal to 1. This is equal to 2 root 2. This is equal to 3 root 3. And this is equal to 8. So now we ask, is this any pattern of arithmetic? Are you adding to the same thing every time, or are you multiplying by the same thing every time? And that's just a big fat no, because this is neither. There's nothing that I can see that we're adding or multiplying by. Lastly, I'm going to do the same style. T sub 1 is equal to 3 to the first plus 1. T sub 2 is equal to 3 squared plus 1. Then 3 cubed plus 1. And 3 to the fourth plus 1. So 3 plus 1 is 4, 9 plus 1 is 10, 27 plus 1 is 28, and 81 plus 1 is 82. Okay, there's no common difference. And let's see, 10 over 4 is equal to 5 halves, and 28 over 10 is equal to 14 fifths. Those are not the same thing. So there's no common difference, there's no common ratio, so this is also neither. It's neither arithmetic nor geometric. It's just a different kind of series or sequence. Okay. This is an interesting style. It says give the next two terms by using the pattern and the differences between terms. This is some very, very solid like intelligence testing here, because we go from 8 to 9 to 11 to 14. Well, what's happening to get from 8 to 9 is that you're adding 1. And you get from 9 to 11, you're adding 2. You get from 11 to 14, you're adding 3. So the next set, we are going to add 4. And you get to 18. Then the next set, we're going to add 5 to get to 23. Here, 5 to 7 is 2. 7 to 11 is 4. 11 to 17 is 6. So the next differences that we do are going to have to be 8, and that's going to give me 25. And the next set's going to be 10, which gives me 35. I'm going to go off to the side here and show you a very interesting result of this idea, and that has to do with numbers like this. Let me write down all the perfect cubes that I can think of. 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 81, 5 cubed is 125, and 6 cubed, let's see, I'm honestly forgetting this right now. I want to make sure I don't mess it up for you guys. It's 216. Okay, so that's 1, 2, 3. Oops, I messed up. 4 cubed is 64. My bad. I knew the one was not right there, but I fixed it before you guys could tell me that. Okay, I'm going to do a difference of differences here. So that's 7. This is 19. 27 to 64 is 37. Is that right? Yeah, 37. This is 61. And this is 91, I believe. Yep. Then if I do the differences here between these, this is 12. This is 18. This is 24, and this is 30. Do you see what's happening? Then if I do the differences, the difference of differences here, this is 6, 6, and 6. Eventually, a lot of, if not all these patterns collapse down to a constant, so that you could always build the next one. I could actually find the next perfect square by continuing this pattern. So I need another 6 here to get to 36. I'm going to use that to get to the next one. So 91 plus 36 is 127. And I'm going to add 127 to 216, and I get 343. And in fact, 343 is 7 to the 3rd power. So it's kind of a neat result, this idea of differences between differences. Okay, back to this. This says now find the value of y that makes each sequence arithmetic. And to do this, we're going to follow that idea that I'm going to take one term and subtract the previous term. And that must be equal to the 3rd term minus the 2nd term. So this is kind of an idea that the 2nd minus the 1st has to be equal to the 3rd minus the 2nd. Otherwise it wouldn't be a common difference. Well, if I can solve this problem, 6 minus y minus 2 and y minus 6, and then I get negative y plus 4 is equal to y minus 6, or negative 2y is equal to negative 10, y would be equal to 5. Number 14, I have not included the parentheses, but there are 3 terms here, and you should see that. So I want to take 4y plus 6 and subtract y plus 8, and that must be equal to 3y minus 4y plus 6. The 2nd term minus the 1st must be equal to the 3rd term minus the 2nd. So I get 4y plus 6 minus y minus 8, and that must be equal to 3y minus 4y minus 6. So then I get 3y minus 2 is equal to y minus 6, or 2y is equal to negative 4, or y equals negative 2. Moving on, we're going to find the ones that make these terms geometric. So instead of subtracting, we're going to do a ratio. This is going to be the 2nd term over the 1st equals the third over the second. So y over y plus 1 equals y minus 4 over y. Well, if I work that out, I'm going to do some cross multiplying. So that gives me y squared is equal to y squared. I'm going to FOIL that, minus 3y minus 4. My y squareds drop out, and I end up with 3y is equal to negative 4, or y is equal to negative 4/3. And then the last one, same idea. 2y minus 1 over y plus 1 is equal to 4y minus 3 over 2y minus 1. Do some cross multiplying, so I get 4y squared minus 3 plus 1, so plus y, minus 3 plus 4, and then minus 3, and that's going to be equal to 4y squared minus 4y plus 1. The 4y squareds drop out. I get 5y is equal to 4, and y would be equal to 4/5. See you guys.